You've been curious about the shape of space? I figured it out. Wrote a paper about it. I wrote this paper about the shape of space back in college, and it still makes sense to me. Nothing's been disproved to me, and I can't seem to get an answer of why this isn't the way stuff is, so I'm going to read it to you. A Naive Man's Universe. Introduction. We are all naive. Since we human beings are not endowed with the sensory equipment necessary to surely determine the true nature of our existence, we don't all perceive the truth of our existence in the same way. Hopefully, we will perceive everything in a way we can be comfortable and happy with, but unfortunately that doesn't always happen. There are many approaches to perceiving a reality. One option is to choose whatever reality you can, want, or feel you have to, and then enhance that choice with complete confidence and total faith. Another option is to again choose whatever reality you can, want, or feel you have to, without then enhancing that choice with unlimited confidence, but instead adhering to the notion that we're fairly naive creatures who are incapable of surely knowing everything. And there's a quote, "Reality is unimpressed with belief." Zarlenga. If you choose the total faith approach, there are both advantages and disadvantages. Faith is a powerful thing. A focused mind, completely certain that what is believed is real, actually makes beliefs become reality for the believer. Hot coal walkers are certain the coals won't burn them, so they don't get burned. Another quote, "Certainty is illusion." Unknown. If creating your own reality by using faith can make you happy and comfortable, then that's great. Faith is a healthy, wonderful thing when it fulfills a real human need to feel loved or when it helps people deal with their mortality. Faith can also be a tragic, unhealthy thing when it makes people live in fear, guilt, pain, or that they live this life for the next. I personally figure we're all kind of naive and there are just certain things we just can't surely know about. I believe that having reasonable expectations of what our capabilities and limitations are is key to making the most out of what we're truly potentially capable of. I think that a reasonable limitation of what we think we can know would be to limit what we consider true to that which we can find truth clues about. It's better to know nothing than to know what ain't so. Henry Wheeler Shaw. There's a good quote. That we're not supposed to know the truth about what I'll call spiritualism, religion. I figure if we were supposed to know about it, we would all know, and there wouldn't be so many different religious belief systems. I don't intend to be attacking anyone's beliefs here, because we all have beliefs, and none of us are qualified to judge which reality is truly legit. I'm just saying I personally rather limiting what I'm gonna have confidence in to that which is perceivable. If there's some higher spiritual level or afterlife, fine, great, in fact. But spending this life concerned about the next seems like a waste of this life. I believe we're supposed to know about this life, things like food, water, earth, sky, and each other. Because here's where we are, and that's what's here. There are certain things we can agree that for our practical purposes we know, such as that the sun is warm. It's not our agreeing that makes it seem truth-like. It's that it seems warm, as best as we can tell with the faculties we've got. The sun may not be warm, but as long as it feels warm to us, for our purposes, it is warm. I figure that the best clues I'm going to find to try and decipher the truth with will be the clues found in the things around me and what they're up to. I look for truth in the furniture of the universe, in nature. Nature knows. That's another quote that I'm attaching to myself. Nature knows. All this was just to let you know where I'm coming from. I titled this paper the way I did because after briefly trying to rap with my current very mathematically thinking science teacher at Rhode Island School of Design about the theories forthcoming, evidently I don't understand any of this because I'm not properly educated. Hopefully my naive perspective has allowed me to approach certain questions from a new direction. Also, as you've probably already noticed, I approach spelling and grammar from a naive direction as well. I don't know if I'm putting this part in because you're not reading it, but Excuse me. Sorry, but I want to stick with the implications of the title. Well, it's a good excuse. To be honest, I'd rather spend the limited time I have on explanations and diagrams than on grammatical concerns. I hope you can bear with it. When in doubt, sound it out. I also need to explain these ideas by retracing the route by which I came to them, so that I can have reasonable justification for turning this paper in as the final project for the science history class I'm currently in. Another quote. The roads by which men arrive at their insights into celestial matters is almost as worthy of wonder as those matters in themselves. Johannes Kepler. Imagination is more important than knowledge. Okay, I'm no mathematician or physicist. I've always been kind of romantically intrigued with what's out there, astronomy and all. In science class, I learned about that Big Bang theory that says the reason everything seems to be spreading apart is that everything used to be together and it all exploded. I learned how things like stars, planets, and even whole galaxies could have been formed from clouds of debris because of the forces that act on such things. That all made sense to me because everything had some kind of perceivable motive. I was all satisfied with that, but I was all kinds of curious about what everything might look like, and no one could seem to cough up a description of it for me that was any more tangible than raw speculation or obscure mathematics. Another quote. In mathematics, you don't understand things, you just get used to them. Come on. Certain issues, such as the size and the edge of the universe, confused and bewildered me, and I wanted to understand. In 1981, when I was about 14 years old, I saw a play in London about Albert Einstein that turned my curiosity into a kind of thirst. I figured I was just going to have to piece together some answers for myself to quench that thirst. I then casually began pursuing a descriptive model of the universe by way of a series of thought exercises. When I began thinking about the universe in terms of its shape, the first options that confronted my approach were the finite and infinite options. It occurred to me that if the universe was infinite, meaning without size limitations, then attempting to chart it would be a senseless thing to even begin to try and do. Certain lines of questioning discouraged me from accepting the infinite option anyway. The notion of an infinite universe doesn't quite agree with Einstein's famous E equals mc squared principle. According to this principle, nothing that has any mass, substance, material, can travel at the speed of light. The only reason that light itself can travel that fast is that if you could slow down a light particle, a photon, and bring it to a stop, it would have no still mass. Photons do have mass when they travel at the only rate natural for them, the speed of light, or c, because mass increases with speed. If we attempt to accelerate anything with mass to c, a Twinkie, for example, the more energy, E, you'd push the Twinkie with, not only would the Twinkie move faster, it will also begin to become more massive, M, which is mass. If it was possible to exert enough energy to push a Twinkie to C, the mass of the Twinkie would have to become infinite. The Twinkie would become everywhere and everything. So no thing can go that fast without it becoming obvious to us. Of course, this conclusion is based purely on the assumption that Albert's equation accurately represents a legitimate principle of nature. Ages of tremendously bright people have provided us with records of their observations and insights. The extent of my admiration, respect, and gratitude to these fellows is great. Not only because all the information my ideas are based on was given to me by them, but also because we all share a common passion. I apologize that I can't credit them all properly for their work. I think that assuming anything is unwise. So after evaluating the reasoning and observable evidence that supports the equation, I figured that it does seem to be legit, and that E probably does equal mc squared. Another seemingly legit observation is that the universe is expanding. Okay, since I wrote this, it may have changed a little. We'll go with it, though. I suggest that you, the reader, evaluate these issues for yourself before assuming that my reasoning is sound. Anyway, according to this expansion, everything is moving away from everything else. Let me expand. And here's my first doodle. A relationship that's well illustrated by our balloon diagram is that the more distance there is between dots, the more space there is growing between them. So the faster they move away from each other. Once we understand this, we can see how the expanding part of the universe cannot be infinite. If it was infinite, then objects far enough away from each other must eventually be traveling away from each other at an infinite speeds, and that's not possible according to E equals mc squared. Of course, that's relative to each other. This gets a little shaky, my thinking here back in college. That whole line of thought apparently made my task infinitely easier. I only had to make a model of our expanding part that could only be so big. So I began to embark on the finite approach. Well, finite. That means that it's only so big. So this is a little break in some good logic, but I figured there could be no place that the universe isn't, if the word universe refers to everything and everywhere. So I thought it must be reflective or turning itself inside out or something. But surely there must be some edge that separates where things are and where they're not if there's a limiting size to everything. But again, there can be no place that the universe isn't. Seemingly stuck in the boundary of size dilemma, I figured there must not be a boundary, meaning a noticeable edge, crease, fold, or wall. Boundaryless, but still finite. A reflective continuum turning itself inside out. Well, that sounded ridiculously vague. I thought on to boundaryless. The best description of a boundaryless universe I'd heard was in that play about Einstein I'd mentioned earlier. It's called Insignificance by Terry Johnson. I'm paraphrasing. Space has no boundaries, but neither is it infinite. That's our starting point. Now consider one dimension first. Consider length without breadth or width. As a model, a shoelace. Consider in one-dimensional terms, the shoelace is obviously not infinite in length, but it does have boundaries. It has two ends. To make it resemble space, it must have no boundaries. So we must tie a knot, get rid of the ends. A shoelace without infinite length or boundaries. A circle, but remember, a one-dimensional circle. It's really a rather unusual straight line. Now let us think one step further in two dimensions. Let's think of something that has length and breadth, but no width. A sheet of paper, for example. A sheet of paper surely isn't infinite, but it has boundaries, the edges. To make it boundaryless, we must make a bubble, a ball, a sphere, but a ball in two dimensions, not three. Only the surface of the ball, as if it had no center or outside, right? Like how you can think of this planet in two dimensions, north-south, east-west. Then its surface has no boundaries, and it isn't infinite either. Now, the next step is impossible to visualize. This is still from this play. We're in three dimensions, and we have to start with a real sphere, a solid baseball. It's finite, of course, but it also has boundaries. Imagine a baseball without boundaries, and you're in the fourth dimension. From a line to a circle, from a plane to a sphere, from a sphere to the shape of the universe. It has to do with motion. The line was given motion through the second dimension. The plane was given motion through the third, and the sphere is given motion through the fourth, through time. The universe is in constant motion through time. You can come closest if you try and imagine turning something absolutely solid inside out and keep turning it inside out forever. Not bad, but it's not quite complete. How can a solid turn itself inside out? Well, let's go back and start with one dimension, a line. There is a curious shape called a Mobius strip that turns itself inside out. It's a twisted loop that, because of its twist, only has one side. If the ant continues along the loop, he will leave his tracks on both sides of it. Well, fine, turning one dimension inside out was easy enough, but is it possible to come up with a shape that can effectively turn the surface of a ball inside out? A one-sided ball? After some time, I came up with a Mobius surface. A tube bends around, and its ends feed into the loops created by itself. The inside becomes the outside. Mobius surface. Solving this step really excited me. When I showed this to a friend, whom I'd often kick around philosophical ideas with, named Eric Young, he bought me a book called Beyond Einstein and pointed out that a guy named Oscar Klein also had a solution for the one-sided ball. The Klein Bottle. Wow, not only was I considering the same issues as some of the big boys, my solution seems better. My science teacher insists that Klein is fine, but I see it as breaking through its own surface, creating an unaesthetic edge. Anyway, back to that last step. To design a Mobius solid, or in other words, a three-dimensional area that turns itself inside out, after a couple of clumsy solutions, I found a shape that did seem to be a Mobius area. It's a fairly familiar shape we've all probably seen somewhere before, called a trefoil knot. Mobius area. Trefoil knot. Well, so what? That line of questioning had seemingly run its course, leaving me with an elegant shape, but no obvious big answers about space's nature. I embarked on a different approach from a different angle. I'd heard about the curve of space, but I wasn't too clear on it. On the surface of Earth, if three people made a triangle with straight lines, we see from outside of the realm of the surface that those lines aren't straight, they curve. The sum of its angles would equal greater than 180 degrees. From what I understood, the curve implied that if you travel in any direction in a straight path, you'd eventually get back to where you started. It occurred to me that knowing the shape of the path around the universe would be key to knowing the shape of the universe. The shape of space's curve is not the same thing as the shape of space. From any starting point on Earth's surface, if you go trucking in any direction straight ahead, you'll return to where you started. A circle is the shape of the path around Earth's surface. The circle describes Earth's curve, but not its shape. Earth is a sphere, not a circle. A higher dimension is necessary to make the transition from the shape of the curve, circle, 2 dimensions, to the actual shape, spherical, 3 dimensions. I thought the Mobius area might be able to somehow describe space's curve, so I began to try and figure out how, from any point in the universe, could this shape, or any other, describe the path light travels around space's curve. Since the transition from Earth's curve to its shape required the presence of another dimension, I figured the transition from space's curve to its actual shape would also require the employment of higher dimensions. The notion that there may be more than 3 dimensions wasn't completely new to me, because I'd heard that for mathematicians to be able to calculate a solution for the grand unified theory, that there must be a 10-dimensional universe. I don't claim to understand why these dimensions are mathematically necessary. I am, however, very impressed with the previously mentioned grand unified theory, GUT. It neatly knits the universe and its forces together in a pure energy state at the beginning. But this theory isn't quite complete. Scientists don't know the nature of this unification. They don't know how Einstein's relativity can be linked with quantum mechanics, which is a vague but astoundingly accurate statistic-like description of the atomic realm. They also don't know how gravity, the tendency of matter to attract itself, can be linked with the other forces because gravity is mysteriously undetectable to us. Anyway, where could all these other dimensions be? Why don't we experience them? Einstein was convinced that time was the 4th dimension because of how interwoven in spatial relationships time seemed to be, but after that it gets foggy. One dude suggested a 5th dimension that curled up and is too small for anything with dimensions to ever be able to deal with. The mathematics of this 5th dimension was evidently quite impressively problem-solving, but somehow it just doesn't flush. There had to be a better answer. The best approach I could think of to find more dimensions was that a curve can only be a curve if it isn't straight. The only thing that can make it an unstraight curve is straightness. Now, I'm getting ahead of myself. The first thing I should figure out is, why is space curved? What possible motive might it have for curving? Then I remembered something about light. Gravity bends it. If gravity bends light, maybe that's why space is curved. It kind of makes sense that all light could be sort of uniformly bending due to all the gravity in the universe. Gravity was the motive, and that's what the curve was. If the three spatial dimensions we know, length, width, height, are warped into a curve because of gravity, then light's path must be distorting our dimensions. Of course, we must be completely used to seeing everything that way, so we don't notice it. Let's say that our three dimensions are better described by the Mobius area than by the traditional straight-lined mathematical XYZ axis. If we compare the dynamics of the Mobius matrix with the dynamics of the XYZ axis, we find that they're actually quite similar. XYZ axis. Connect the ends, eliminate the center, Mobius area. Maybe the shape of space can be legitly mapped if you remove yourself from the warped, curved continuum by introducing three more dimensions that aren't warped by gravity's influence. How could I justify these straight dimensions? Here's a quote. Einstein once wrote, "I believe that in order to make real progress, one must ferret out some general principle from nature. No matter how hard he tried, however, he could not think of a new physical principle, so he became obsessed with twisted geometries and ultimately failed to create the unified field theory." From Beyond Einstein by Michio Kaku and Jennifer Trainor. One general principle that could justify the straight dimensions would be if gravity bends light, as we observe, but it doesn't bend itself. It didn't make sense to me that a force, being that which can change the momentum of a body, would ever work against itself. You see, not only does gravity bend light, it also slows light. Photons naturally travel at c unless something interferes with them. When light is emitted from a source like a star, the gravitational field of that source actually slows the rate of the leaving photon until it gets beyond the strength of the field, or can attain its speed. If the gravitational force is also composed of waves of particles, as it is widely accepted, then it would have to bend and slow itself, because as a particle, graviton, it'd have mass. How could gravity be a particle? I don't buy any of that. I mean, photons are created by atomic reactions that produce and shed them. The creation of the photon's mass is noticeably accounted for by the change in the mass energy state of the involved particles. There's no observable reaction that should emit gravitons. If mass just creates gravitons without somehow losing the amount of mass energy that gravitons are, then that completely contradicts the conservation of energy matter laws. Gravitons have no motive for being particles, so I figured that a different gravitational explanation was necessary. If gravity isn't a particle, what is it? By what medium does it travel long distances, and at what speed? The question of what would happen to Earth if the sun instantaneously vanished has been posed to answer these questions. When would Earth notice the missing gravitational field of the sun? We can figure we wouldn't see the sun vanish for 8 minutes because light takes 8 minutes to travel from sun to the Earth. But how long would it take for the Earth to swing out of orbit of an object that's no longer there? Einstein tried to visually decipher an answer by using a diagram of a trampoline with a large weight object in the center. From this diagram, it was concluded that if the weight, sun, was instantaneously removed, the news of its absence would travel along the tramp in a wave at the speed of light. Well, that conclusion wasn't so obvious to me, so I tried to simplify the diagram so that it might be clearer. First of all, the notion of suddenly removing the weight was cluttering the clarity of the diagram for me, so I figured instead of an object on top, why not just pull it down from beneath, right? That way, by releasing the tramp, the force holding the tramp down could instantaneously be neutralized. Great. Now, instead of that cloth tramp, why don't we just continue those springs all the way? It seems that the moment the pulling force is neutralized, the forces that still affect the spring immediately began the overtaking process. The rate of overtaking seemed to depend on the strength of the spring and the strength of the pull that was neutralized. When the spring is released, news of the release gets diffused and distributed along the length of the interconnected other forces. Well, that still wasn't clear enough for me, so I pictured a dude dangling a barbell from one end and dropping it. When the guy on the ladder releases the barbell, the whole barbell immediately plummets downward. Now, that was a little clearer. The entire barbell is connected together, so the whole barbell is released at once. News of the release does not need to travel to the far end of the barbell. Maybe gravitational fields are interconnected like this somehow. How could gravitational knowledge move faster than light? Well, if it's not a particle, then it would be immune to the E equals mc squared constraints, and the mass-speed correlation is non-applicable. But what is it? Does it even need to travel at all? I propose the reason gravity is so mysteriously unobservable is that gravity dwells in a higher dimensional realm, a straight realm, unbent by itself. Gravity is just some kind of interconnected field of attraction that mass energy is inherently endowed with. Mass has a territory. That's the pattern of pine cones, pineapples, sunflowers, daisies, etc. These spiraling lines had no excuse to ever end. The further away you are, the less probability is you'll encounter a line of influence. Now, my understanding of quantum mechanics is embarrassingly vague, but this sounded like the fields of probability used to describe the semi-mysterious nature of the electron in atoms. Maybe a quantum theory of gravity can be employed to describe gravity. This whole theory of gravity is still semi-mysterious, but at least the nature of why it's mysterious is explained. If there are our three visual dimensions, light, and then three actual spatial dimensions, and sure, time is the seventh, then where could those remaining three required dimensions be? For the mathematics of some guy's equation somewhere? I propose that there are three more dimensions at the atomic level, nuclear dimensions, because when scientists describe atomic activity, gravity simply isn't involved for us. This explanation of where the 10 dimensions are seems to explain why quantum mechanics can't be linked with relativity. Quantum mechanics can only be observed to describe extra-dimensional phenomena. We, in our three visual dimensions, observed relativity and can't observe any quantum mechanic effects. They can't be linked because they're in separate dimensional categories. To help support the application of this extra-dimensional matrix, I had to figure how the Mobius area, or any other shape, could describe the curved path light travels around the universe in. It had to work from any point within the area covered by the universe. It is mapped on the sixth-dimensional matrix. Boy, this sounds a little more complicated, but stick with me. It's all going to make sense here. Like how the circle works to describe the path around Earth's surface from any point in any direction. Well, as soon as we put the center of our shape anywhere near the edge of where the universe is in straight dimensional terms, we're apparently screwed because light would go where the universe isn't. Outer vantage point, near edge. Where stuff is, in straight dimensional terms. Realm of vision's curved coverage. Well, if gravity bends light, shouldn't more gravity bend light more? A gravitational field is strongest near the outer edge of the mass that creates it. At A, gravity pulls you from many directions. At B, all gravity pulls you in one direction. At C, gravity's in one direction, but the distance weakens the field. Here's another quote. Every particle in the Earth that possesses mass, every proton, neutron, and electron, is the source of a tiny gravitational field. and all of them melt together and add up to the overall gravitational field of the Earth. From The Collapsing Universe by Isaac Asimov. Similarly, all the gravitational fields in all of the stars in a galaxy melt together, adding up to the overall field of that galaxy. Shouldn't every gravitational field in the universe add up to one cohesive universal field as well? According to this reasoning, light's curve couldn't be constant. It must curve more radically closer to the edge, where the overall gravitational field of the universe is strongest. At A, gravity's all around, gradually bending light. Finite area covered by the universe. At B, all gravity's in the opposite direction of the edge, bending light back more drastically. Wow, this was the first explanation of why we can never encounter the edge that made any sense to me. Whenever you look towards the edge of where things aren't, your line of sight gets redirected towards things are. Apparent visual location of a star from A. The edge. Actual location of a star. More gravity at A, like a sprinkler on Earth. Less gravity at B, like a sprinkler on the moon. Light leaves a source like water leaves a sprinkler. The curve isn't uniform, but gravity alters it to appear uniform as a seemingly constant continuum without an edge from anywhere within. If you ask what's beyond the edge there in that diagram, I'll cleverly answer nothing of our 3 known dimensions. After coming up with these latest diagrams, I realized the Mobius area was no longer cutting it. The sprinkler diagram was only describing light leaving a source, and it didn't describe light's incoming route. So to figure where it comes from, I needed to know where it goes. I decided to logically follow light leaving a source on its course established in the last diagram. To do that, I'm going to have to include some notions that have been up to now unaddressed, namely time and space-time. At this point, I'd love to completely delve into how actual dimensions affect relativity and how it clears up all those not aging, meeting yourself as a baby type issues. But right now, I simply don't have the time. A due date is rapidly approaching, and my other film animation classes require some major attention. I can bypass this and complete the description of the curved dimensions and life of the universe by establishing one simple principle on which relativity is based. The principle is that light takes time to travel, so the deeper in space you peer, the further into the past you're observing. The farther away from us an object is, the longer it takes for that light to travel to us, and the older, more historic, that light and the image it brings us is. With this in mind, we can conceivably chart our possible range of vision, with us at the present and things further away deeper in the past. Another possible difficulty with this diagram arises when we consider that the universe is expanding. The universe must be bigger now than it once was. If that's so, then it's quite possible that we are now located somewhere where the pre-expanded universe didn't used to be. Well, shouldn't we be able to look far out into space and far back in time to when the universe wasn't there yet? You are here. Area covered by expanding universe today. Area of universe before it expanded. Range of vision. It seems that you wouldn't see the pre-expanded universe in every direction, and that you'd be able to see outside of the universe. This seeing outside of the universe problem is solved by graphing life's curve on my higher dimensional matrix. Sprinkler-like, drain-like. You couldn't see out where things used to not be, because light bends around to the gravitational center, guiding light back to where things did used to be. You would see the Big Bang in every direction. Well, there went the whole idea of looking out and seeing the back of your head. When you look out, light zings toward the gravitational center, and it will never come back. The only apparent edge to anywhere within is the center, or historically the beginning. The shape of light's curve is not a circle, nor a Mobius area. It's tear-like, or if everything's rotating, it'd be more like a three-dimensional paisley. This seemed to predict that the Big Bang should be a little closer in one direction. But no, wait. This isn't light coming in, it's the light leaving. Well, if light leaves all sources in this sprinkler-like fashion, with the intensity of the curve being proportional to the location of that light emitting source within the overall gravitational field of the universe, then it makes sense to figure you can see only those sprinklers that are getting you wet. Well, I decided to picture a sprinkler fountain sculpture kind of thing to explore the nature of what we can see by figuring out what sprinklers get each other wet. Getting kind of complicated. This is our fountain, where there is always the same amount of water and pressure being pumped into each spout. We can simulate the different reactions of light in the different gravitational field locations by changing the size of the holes of the spouts by rows like this. Row 1, big holes, strong field. Row 2, row 3, small holes, mellow field. The smaller the holes are, the farther the water travels. Just like how you can make a hose spray further by putting your thumb over the spout. When two spouts are in the same row, same gravitational intensities, their curves are the same. If they move towards each other, as soon as they get close enough for one to get the other wet, they'll both get each other wet at the same time. This simply implies that if you can see it, it can see you. Any diagrams beyond this point concerning the interrelationships of objects and how their lights curve are simply too raw to serve now. This whole description of light's curves within the universe seems similar to the description of light's behavior within a black hole, in that no light can ever escape from either. Diagram of light draining into a black hole. A black hole is a theorized hyperdense collapse thing that has a gravitational field so strong that photons can't escape from it. Their escape velocity. Why do I think light goes whipping to the center with so much motivation? After all, everyone knows space is uniformly covered with stuff. What could light be draining into at the center? This question seems to answer itself when we consider the life of the universe. Again, by leaving our visually warped dimensions and charting where things are on the actual dimension, we'll start at the moment of birth, the Big Bang, the moment of unification. What was it like? Then it exploded in a big way. I'm going to go out on a limb and assume it blew apart in the same way every large cosmic body blows apart. Most of its mass blew out in a shell of expanding stuff, polka dot balloon. And some of its mass remained, crushing in on itself, either to re-explode or settle into some hyperdense core. If it did re-explode, there would again still be a remaining core that would again collapse to re-explode or settle. No matter how many times it re-explodes, eventually a hunk would settle, and this hunk is at the gravitational center of everything, exactly where everything was before it exploded. This is where all the light gets sucked to. What will happen when the universe gets to where it's going? Will it continue to expand forever? Will it reach an equilibrium and spin dead forever? Or will it recollapse on itself? Since the rate of expansion seems to be slowing, a figure can't expand forever. Now, again, recently people have debated if it's expanding or closing or what's going on with it. So, what it will be like. Big, cold, pure matter, slow, possibly rotating, dead, no energy. All right, we're almost getting to the end here, but I thought this was the biggest paper of my life, so I covered everything.